Hello students, myself Dr. Yuhit Gupta. I want to thank you because our Telegram channel has completed 100 members. Thank you so much guys. Now without wasting any time, let's move on to our next topic in which we will study the binding energy per nucleon. In the graphical representation form, we have drawn a curve along the y-axis. We have plotted binding energy per nucleon, and on the x-axis we have plotted mass numbers. Now let's study what is happening in this binding energy per nucleon curve. First element that is representing this binding energy per nucleon, it start basically with the deuteron, because binding energy we will study first of all for the deuteron nuclei. Now for this deuteron nuclei we will see it is having value of 1, like near about value is binding energy per nucleon. Now we are studying the binding energy per nucleon, not only the binding energy. So whatever we have calculated the binding energy per nucleon, we will divide it by the number of nucleons present in the nuclei. Like in this case of deuteron, it is 1H2. The binding energy for this is I think 2.23 MeV. Now we have to calculate the binding energy per nucleon, so we will divide it by 2, so it becomes 1.11 MeV. Okay, now this is the binding energy per nucleon for the case of deuteron. We have also already plotted for the case of helium, lithium, carbon, nitrogen, oxygen, and for all the elements present in our periodic system, like with the mass numbers. Okay, now what we will see binding energy per nucleon curve between binding energy per nucleon and mass number, that some nuclei like helium nuclei, carbon nuclei, oxygen nuclei, they are showing peaks, and while others are showing dips in this curve. Now we can conclude from this that the nuclei having the mass number which are multiples of 4, they are showing higher value of binding energy per nucleon. Means higher the value of binding energy per nucleon means they are showing the stability of these nuclei. Means these nuclei are much more stable than that of the lithium and nitrogen and all other elements which are present all around these nuclei. Now we will also see a highest value of binding energy per nucleon is observed in this case of iron nuclei, because iron nuclei is showing a highest value, so we must need to remember it, because sometimes in exam examiner may ask about which nuclei is showing maximum value of binding energy per nucleon. So we need to remember the value also, which is 8.8 MeV, and also about which nuclei, which is iron, which is 2656. It might be occur that examiner may ask about it might occur that examiner give you 4 options like with their isotopes. So you must also remember 26 Fe56, which is showing the maximum value of this binding energy per nucleon. Now we will see that in the case of uranium, which is a much more heavier element than that of the iron, the binding energy per nucleon is less than that of the iron, which is 7.6 MeV per nucleon. For helium, it is 7.2 MeV per nucleon. Now let's study what we are concluding from this binding energy per nucleon. First, we have already studied that the binding energy per nucleon for the nucleon having the which are the multiples of 4. We have studied the peaks there. Peaks representing the higher value of binding energy. Higher the value of binding energy, higher will be the stability of those nuclei. Now the second conclusion that we can observe from here is the binding energy per nucleon for the nuclei which are lighter in size, like they are having the value of mass number less than 20, they are showing small value of binding energy per nucleon. than the other nuclei. Second, medium sized nuclei which are having mass number which are lying between 20 and 80, they are showing a constant value. Like we can say in this reason it is approximately constant. Approximately constant binding energy per nucleon is not either decreasing nor decreasing. So we can say it is approximately constant. And third conclusion that we can draw is in this higher sized nuclei we have observed that the value of this A, like number of nucleons which are greater than that of 80, the binding energy per nucleon starts decreasing. For this reason it is decreasing, and from the whole picture we can study that for the nucleons having A less than 20 it is also decreasing, for A greater than 80 it is also decreasing, and it is approximately constant in this region from 20 to 80 nucleons. Now the question arises why this is happening. Now if we'll study for A less than 20, for the smaller the value of nucleons, like we can say smaller the value of A, smaller would be R, because R and A are directly proportional to each other. Nucleons will be present more on the surface. Now in this case with the nucleons less than 20, all the nucleons we know that they are present inside the nucleus, but when they are small in number they all will be present on the surface of the nuclei, inside the nuclei, and their tendency to move out of this nuclei is very much higher, means they can escape easily, so the stability decreases. Stability decreases means binding energy per nucleon also decreases in this case. Now let's study why it is happening constant, why binding energy per nucleon is constant in this case, A lying between 20 and 80. Now what is happening in the nuclei for number of nucleons lying between 20 and 80, we will see there are nucleons which are present on the surface. Now in this case the nucleons present inside the nuclei are much higher than that present on the surface. So inside the nuclei, nucleons can easily undergo exchange of pi mesons. As we know, whenever there is an exchange of pi mesons which lead to the nuclear force, means there is a stability, and more the value of stability, more will be the binding energy, and the binding energy becomes constant in this scenario. Now let's shift on to what is happening in this case for higher nuclei, that is A greater than 80. A greater than 80 means the value of A is increasing. As the value of A is increasing means number of neutrons are also increasing and number of protons are also increasing. Although neutrons are neutral, but number of protons are increasing inside the nucleus. When the number of protons are increasing, which results the repulsion force, and repulsion led to the decrease in the binding energy, because when there is a repulsion between the protons, they can easily they can have a tendency to move out of the nucleus, like they want to escape from the nucleus because of the repulsive force. So binding energy decreases. So the three conclusions that we have drawn, we have studied deeply. Now the last, we must remember these numbers 2, 8, 20, 28, 50, 82. I want all of you to speak loud with me while watching this video, these numbers. In this way you will remember these. First is 2, second is 8, third is 20, fourth is 28, fifth is 50, and sixth is 82. These are the magic numbers. The nuclei having these mass numbers, they are having the higher value of stability. Now what is happening? Why these magic numbers are showing the higher value of stability, like higher value of binding energy? Because in these cases the we can say the number of nucleons are mostly, they are even in numbers. Okay, now they can be treated as they are having even nuclei, like their spins will cancel out and they lead to the stability. So this is all the conclusions that we have drawn from this binding energy per nucleon. This is very much important in case of conceptual questions that might be asked from this curve too, because in syllabus they have just asked about binding energy. Understand, we have to study each and every topic which is related to the binding energy. Either it's binding energy per nucleon curve, or it's binding energy calculations, or any other thing which is related to the binding energy. Now I want to discuss some few questions which are based on this binding energy curve. First one is, why helium atom shows peak in binding energy curve. Helium nuclei contains 2 neutrons and 2 protons. They are having net spin is equal to 0 because one proton is having up spin and other proton may have down spin. Similarly, one neutron have up spin and one neutron have down spin, so the net spin becomes 0 and net spin becomes 0, which led to the higher value of stability, and it shows a peak in our binding energy curve. Second, in the case of carbon, we can say number of neutrons are 6 and number of protons are also 6. In similar to this helium, we can say the net spin in this case is also 0, which led to the stability. For the case of uranium, it is 7.6 MeV. This is again for the net spin is equal to 0. Now next question, why we are plotting curve between binding energy per nucleon, not between binding energy not between binding energy and number of nucleons. Now the question arises is, if we just calculate the binding energy for this our deuteron, which is 2.23 MeV, and for our uranium it is 1800 MeV. But we have studied here that for uranium binding energy per nucleon is 7.6 MeV, and but binding energy completely it is 7.6 into number of nucleons present, so it is 1800 MeV. So if we try to plot curve between this, like this is 2.3 and this is 1800, it will go a very long and we can't even study it completely, so range becomes wide and study becomes difficult. That's why we have plotted curve between binding energy per nucleon and number of nucleons instead of binding energy and nucleons only. Now the next question arises, why does energy release in case of nuclear fission and nuclear fusion? Now what is happening, this question is very much conceptual, because on this basis examiner may ask question by giving some plot or some equations. So you need to remember this case, either it is a nuclear fission or it is a nuclear fission, there is a release of energy. Now why it is happening, like we can study for the case of uranium 92 to 35, when we strike, like we have studied in the class 9th or 10th, like this is known as a chain reaction. When we have struck one neutron on this uranium atom, it turns into uranium 236 and it will already gives you two more elements, that is barium and krypton, and with the three more neutrons. Now the with the 200 MeV, the release of 200 MeV energy. Now what is happening here, like we will calculate the binding energy per nucleon for these barium and krypton, which is 8.5 MeV, and for the uranium it is 7.6 MeV. And when we find out the difference between these two, we will get some release of energy. So there is a release of energy when a heavy nuclei results to undergo nuclear fission, there is a release of energy. I think this is sufficient for today, otherwise video becomes very long. पढ़ते रहिए, खुश रहिए.